Hey everyone, my name is Jason Gaitonde, and I'll be telling you about our work on polarization and geometric opinion dynamics here at EC 2021. And this is joint work with John Kleinberg and Eva Tardos, both also at Cornell. So the motivation for this work is understanding mathematical models of opinion dynamics. And so the idea is that people's opinions evolve in response to their environment from many factors, namely either interacting with other agents, so you think of them as lying in some sort of network, or they can evolve in response to some sort of random events, or they might evolve according to some sort of political process like elections or some new political figures show up. And the goal of these models is you want to understand qualitative features of these dynamics. And one phenomenon that's been of recent interest is that of polarization of beliefs. So here's a very interesting figure from some recent work of Genskow, Shapiro, and Tati, which shows the ability to predict party affiliation from 1 minute of political speech. So these bottom two lines show that basically from around 1817 to 1990, the ability to predict party affiliation from 1 minute of political speech was just a little bit better than 50-50. But if you fast forward to 2007, the ability to predict party affiliation from political speech actually just skyrocketed. So at least in terms of, say, expressed opinions by American political figures, it seems like this has sharply polarized in recent years. But when we say polarized, what we're going to mean is that agent beliefs are clustered on opposed beliefs, as opposed to occupying a rich spectrum of beliefs. And a related phenomenon here is that of issue alignment, where we have correlations between issues that you might think are a priori unrelated, say things like climate change and gun rights. And one kind of feature of classical models of opinion dynamics is that many of them are based on repeated averaging. And such models are almost inherently contractive, meaning that the effect of them is that opinions will tend to get closer over time than they were at the beginning. And such models, at least without some appropriate modification, seem not super well equipped to study these phenomena like polarization. Another motivation for our work comes from this really interesting model of Hasla, Jin, Mosel, and Ramnarayan, who I'm going to call HJMR from now on. And they introduce a novel and elegant model that really studies these phenomena at length. And so what they do is, in their model, opinions are multidimensional, and they're going to evolve on the hypersphere SD-1 for d-dimensional opinions. And the idea of their model is that agents are going to move towards or away from some new random stimulus CT that's drawn from some fixed distribution. And the amount you move towards or away from it depends on the sign and correlation with the current opinion. And what they actually show is that in special cases, namely for two-dimensional opinions, and when these CT are drawn from, say, the uniform distribution on the unit circle, any two starting opinions they're going to asymptotically converge to the plus or minus of each other. So you get actually a very strong notion of polarization in this special case. And I think the argument's really nice, so I just want to quickly sketch it out for you. So opinions are going to lie on this unit circle. So x01 and x02 are two different opinions by two different agents. And now this new random issue shows up at time 0. And so each agent evaluates the sign and correlation of their inner product with this new random issue, and they'll move accordingly towards or away from it. And then what they're going to do is, for the next period's opinion, they now project back onto the unit circle. So the new opinions are x11 and x12, like so. And so a sketch of how polarization arises in this model is that, because you should think of angles here as of one-dimensional quantity because d equals 2. And it turns out that something like linearity of expectation and this uniformity of the random issues is going to imply that the angle between any two starting opinions will form a martingale. And this is the step that kind of crucially relies on this d equals 2 and uniform distribution. And then as a consequence of the martingale convergence theorem, it's a fact that the angle must converge to a limit with probability 1. But the only kind of stable values for possible limits of this are 0 and pi, which means that the opinions either asymptotically go towards each other or to diametrically opposed. And that's how polarization arises. And so the goal of our work is to kind of understand how general is this strong polarization. In particular, the things we want to understand are, can it hold in different conditions? And can it hold in maybe more robust settings, so in higher dimensions or with non-uniform distributions? We also kind of want to understand how this interplays with network effects, because in this HJMR model, the two opinions kind of operate in isolation, just where they share this common random issue that shows up at each time, but they're otherwise oblivious to each other. And we also kind of want to see if there's different techniques that maybe don't need these uniformity or symmetry assumptions. Something else that we'll be really interested in is, are there weaker forms of polarization that are interesting? It's not so hard to come up with some natural dynamics that don't polarize in such a strong way, but it might still be the case that there's other interesting and provable forms of polarization that hold, even when this strongest notion doesn't hold. So with that in mind, we can actually generalize the dynamics of HJMR as follows. We'll have n agents with opinions we're going to collect in this tuple xt equals xt1 through xtn, where xti is agent i's opinion at time t. And agent I is going to update opinions according to the following rule. Their opinion at time t plus 1 will be proportional to their opinion at time t, plus some function of the tuple of all agents' opinions, and this new random issue ct that's drawn IID from some distribution. And with this definition, you actually just get a Markov chain. And we're going to say that a set of opinions are polarized if all the components are equal up to some signing. And so again, here's the update rule from the previous slide. And some examples of this are, again, the original HJMR model, where the form of this fi function was eta times the inner product of agent i's opinion with ct times ct. Here's another one, the signed HJMR model, where we replace this inner product with a sign. So it's kind of like an all or nothing version of the HJMR model. And here's a model with network effects. And the idea is that you're going to move towards people on the same side and away from people on the opposite side. So the notation's a little cumbersome, but the idea is that CT defines a hyperplane, where people with positive inner product with that CT are on one side, people with negative inner product are on the other side. And what an agent I is going to do is they're going to move to some weighted average of the opinions of people that are on the same side of the hyperplane, and away from some weighted average of the people that are on the opposite side. And so these eta ji multipliers here are going to be these sort of network effects, and they measure the strength of the interaction between agents I and j. And so with this in mind, the way we can define strong polarization is as follows. Some geometric opinion dynamics model will strongly polarize if it's the case that from any starting configuration x0, this tuple xt of agent opinions at time t converges to this set p of polarized vectors almost surely. And so to restate the theorem from before, the HJMR dynamics strongly polarize for d equals 2 in the uniform distribution over the CTs. And so one of our main results is the following. If the distribution is actually equivalent to uniform, meaning that the probability of any event in this measure can be upper and lower bounded by some constant of its probability under the uniform measure, then actually both this signed HJMR model and this party model that we defined previously under some mild conditions will strongly polarize in any dimension. And to do this, we're going to use some different techniques. And I want to point out that there's actually no need for the strong symmetry assumption in this distribution D. Any equivalent measure to uniform will do. So let me sort of sketch how this works in the party model. The first actually very general reduction we show is that, again, to show strong polarization, we need it to be the case that from any starting opinion with probability 1, it converges to polarized. But it actually turns out to be sufficient to show that from any starting opinion, there's some uniform lower bound on the probability of this polarization. And the intuition for why this is actually sufficient is that imagine for a second that we were in a finite state Markov chain, where polarized is just an absorbing state of the Markov chain. In that case, to show that the system reaches polarized, all we would need to do is that any state has some non-zero probability of reaching it. So in general, this doesn't hold true because we're not in a finite state Markov chain, and polarization is actually more of an asymptotic condition. But it turns out that you actually can show that this is true using a different 0-1 law, namely the Levy 0-1 law. Another actual general reduction is that we can actually assume that each of the starting opinion vectors in x0 lie on the same side of some hyperplane. So you can actually assume that the starting configuration looks a little bit like this picture below. And so the key idea of the proof is this kind of interplay between probability and geometry. And so what you can show is the following. Suppose it's the case that the maximum angle between any two vectors, these agent opinions, decreases by a geometric factor when none of them are split up by this CT. Then you can actually show that the probability of polarization is lower bounded by a constant, in which case the general reduction from before will imply the system strongly polarizes. And the reason for this is sort of the following. Let's just consider two opinion vectors, x01 and x02. Whether CT splits these two vectors up depends just its projection on the plane spanned by them. And our assumption on the distribution D and its equivalence with uniform implies that the probability of splitting it up is actually it's at most O of the angle between these two vectors. And in particular, if it's the case that every time they don't get split up, this angle decreases by a geometric factor, then the probability of splitting up is actually decreasing by a geometric factor. And by some sort of standard analysis tricks, this will actually imply this constant lower bound of polarization, which will be enough. So as a result of this, it actually just suffices to show this geometric contraction of angle when none of the vectors get split up. So to do this, let's suppose that these multiplier terms are all uniformly lower bounded by some positive epsilon. And let's consider this potential function phi that takes in x1 through xn. And it takes the best vector v that minimizes the maximum angle of v with any of the xi's. So this potential function is actually equivalent to the maximum angle between the x1 through xn up to some constants. So it'll suffice to actually show geometric decay of this function. And so there's a couple of ways to show this, but a really nice simplified analysis that was communicated to us by Ron Peretz is that you can show this geometric decay where the constant depends on just n, d, and epsilon, but not on the starting configuration, by considering the projection onto this optimizer in this potential function, the best v here, the projection onto that optimizer, as well as the orthogonal subspace separately. And you can do this, and you can actually obtain this geometric decay, which by the reductions before will be enough to show strong polarization. So now, okay, so we just argued that strong polarization holds in related settings and under some very robust assumptions. But again, we had this question of, are there other meaningful notions of polarization? And the answer will be yes. So here's a different notion. Here's a notion we call weak polarization. Suppose it's the case that for every epsilon greater than 0, the probability of being epsilon far from the set of polarized vectors is little o of 1 with time, so it's decaying with time to 0. A different notion is weak polarization on average, which is that for any epsilon greater than 0, the time average probability of being epsilon far from polarization is little o of 1. So what you can actually show is these notions are kind of meaningful, and you can actually show the following theorem, which is that suppose we have continuous update rules, so the fi functions that dictate the dynamics are continuous in the arguments, then it turns out that weak polarization on average is actually equivalent to all invariant distributions on the Markov chain being supported in P, the set of polarized vectors. So again, there's kind of trivial examples where strong polarization fails. So for instance, imagine the updates are such that there's kind of a common orthogonal update to all the vectors, in which case the distances don't change. So are there examples where weak polarization holds, but the strong form doesn't? And we actually show that this is the case. And in fact, it holds with this HJMR model where I have orthonormal updates. So the CT will be uniform on basis vectors. So what we show is actually for any starting configuration, say x01 and x02, that has full support in each component, so each component is non-zero, and these two vectors are not equal up to sign, then it'll be the case actually that the system weakly polarizes, but almost surely does not strongly polarize. So with probability 1, they actually won't converge to plus or minus the other. And the way this kind of works is actually in this setting, this very special setting, you can show that the updates are commutative in a particular sense. So the location of the vectors at time t sort of depend only on the multi-set of the CTs that have shown up till that time. And so under this fact, the proof will actually reduce to some sample path properties of infinite balls and bins processes. And to do this, we'll actually use a different 0-1 law, namely the Hewitt-Savage 0-1 law. And so what you can show is actually with high probability, any two starting vectors under our assumptions will be close to some common basis vector, either plus or minus of some common basis vector. And this actually means that the system is weakly polarizing, as we claimed. But using these sample path properties of infinite balls and bins, you can show that the configuration is infinitely often as far away from each other as it was in the initial configuration with probability 1. And so what this means is it can't possibly strongly polarize. So just to summarize what we've talked about, we study a generalization of these HJMR dynamics. And we show that their notion of strong polarization actually holds in some related variants, but without some of these symmetry assumptions and in any dimension, and in one case with network effects. And we also talked about some weaker, but I think still interesting notions of polarization that can arise in these geometric opinion dynamics. So for some future directions, a really nice thing that would be ideal to have is that can we find more general and easily verified sufficient conditions that will imply strong polarization? And in particular, it's still open whether this HJMR model strongly polarizes for higher dimensions. I'd be interested if we could establish some very general conditions that even capture this open case. And maybe a more meta question is, are there other kind of nice different probabilistic tools we can use to understand these questions about polarizations in such models? So with that, thanks so much for your attention.